Hello everyone, welcome back to Calculus, and we are doing the introduction of the concept of limits. It's from section 2.2, and remember those 3 charts, 3 graphs, and basically they represent 3 different cases of limits. In this case, we do have a single limit. And in the second case, believe it or not, we say we do not have a single limit, even though there are 2 one-sided limits. And in this case, we say there's the infinite limit. Okay. And then many times, as you can tell, given a function, a mathematical function, usually we really don't have the graph. Usually we don't have the graph. Then how do we get the limit? How do we get the limit? So the second way at this moment to figure out a limit, to observe a limit, it is simply by trying different values for the function. So this is the next example, and in this case, even though actually x squared minus 4 over x minus 2, really, this is the graph right here. The graph we already did, okay? We understand that there is a limit for here, okay? And now let's pretend that we don't have the graph, and let's pretend that we don't get anything from the graph. And we take a look at how we can figure out the limit using the numerical values. So it is considered as x approaching to 2. And what I did here is actually the table has 4 columns. Actually, it is separated in 2 halves. The left half has 2 columns. The first column, it is for x values. And second column, it is for the y values. And we understand x approaching to 2 could happen in 2 ways, 2 directions. Okay, any x approaching to 2 from right, which means all the x values are bigger than 2. So this is what I tried. I tried x at 2.1, which is bigger than 2. And to make it approaching to 2, so I tried a 2.01. Then I tried a 2.001. And I got more zeros before the 1. So then what I did at the calculation, okay, for this function as x approaching to 2, and the calculation, what I observed here is 4.1, 4.01, 4.001, and certainly there will be more zeros if you add more zeros for the x values. So it's fair to say, as x approaching to 2 from right, the limit it is. The function value, it is approaching to 4. The function value, it is approaching to 4. Okay, the second half of the table really similar situation. But anyway, hopefully you see, I'm trying to try those x values approaching to 2 from left. They are always a little smaller than 2. Okay, 1.9, 1.99, and then add more 9s. And then surprisingly enough, okay, the function value as x approaching to 1.9, 1.99, x approaching to 2, the function values, they turn out to be 3.9, 999, 9999, these things, right? So it's fair to say, as x approaching to 2 from left, all these numbers, indeed, they are approaching to 4, And this is exactly what we observed from the graph. The numerical value we observed from the table and the limit we observed from the graph. They turn out to be the same. And again, this is exactly the situation as I'm saying. When we have a limit, there got to be one single limit. Cannot be 2 limits. Okay, cannot be 2 limits. So we have a case. We are having a limit right here. The limit it is 4. Maybe I should add here. I should add a number. The limit conclusion as a conclusion limited is 4. Limited is 4. Okay. And next part. Actually, I did not get the graph here, but anyway, I'm trying to show, somewhat using numerical value, it is more powerful. It is very powerful. Okay, it is very powerful. We are considering the limit of sine x over x here as x approaching to 0. So this is how I tried. And I try x approaching to 0 from right. So I have those positive values. They are greater than 0. And surprisingly, sine x over x, now I say, even though those numbers may look weird, but anyway, it's fair to say, looks like they are approaching to 1, right? And also at the same time, I did try for those smaller values. Well, x approaching to 0 from left. Those negative x values. But anyway, they are still approaching to 0, right? From left side. And not surprisingly, sine x over x, still it is approaching to 1. Approaching to 1. So overall, the conclusion, it is this limit, it is approaching to 1. And also, if you are watching the video, as I'm saying, do yourself a favor and do me a favor, write this down. Write this limit part. Write down the conclusion. Write down this conclusion. And we are going to see this limit multiple times in the course of Calculus 1. This is a very important limit. Okay, this is a very important limit. And also, this is another reason I want to say this is a very important limit. And you may want to know, and I should have mentioned, the limit of a function really reflects overall the pattern or the behavior of the function around this point. It may not have anything to do with the function value, like in this case. The function value does not exist. And also, the behavior of the function from left and right, they could be different. And if that is the case, there's not a limit. And also, this is kind of extreme case. The limit turns out to be infinity. Okay, we'll talk about this other case again. So this is basically a very intuitive approach, very intuitive introduction of limits. You really need to try a few more examples on the textbook, or you can try those homework assignments first. And also, the numerical values are very helpful. And any chance if you have the graph, and you could possibly see the limit from the graph too. So let's try a little more. I think I have some more examples here. Yeah, this may be the example. It is to evaluate a limit using a graph. Actually, this is just the example from section textbook 2.6. And before I show you any part, let's try to see if we understand the graph clearly. Okay, that is not a specific formula. Basically, this notation means we want to find a limit as x approaching to -1. And this is given as a graph. And again, when you see empty circle on the graph, it simply means this empty circle, it is not a part of a graph. But the solid dot is. The solid dot is part of the graph. Okay. So here is what I see. First of all, I didn't recognize the empty circle, it is not a function value. But the solid dot is. So I said g of -1, the function g at x equals -1 is 4. Okay. And then when I observe the limit, I trace the curve for x values approaching to this -1 from left. And would it make sense to you? Trace the curve for x values approaching to -1 from left. I am seeing everything. It is being pushed into this little empty circle. So this is my conclusion. Limit as x approaching to -1 from left. It is approaching to -3. And also, actually, it should be approaching to +3. I typed this wrong here. Okay. Also, I hope you see as x approaching to -1 from right, it is approaching to the same empty circle, right? So I simply put the limit of this function, it is 3. And again, I want to tell you, in general, the limit may not have anything to do with the function value. Clearly, in this case, the limit is different from the function value. And again, keep in mind the limit really it is the reflection of the function behavior around this point. Around this point -1, not necessarily the function value. Certainly, you will see many times the limit does match the behavior of the function around the point. It doesn't match the function value exactly at the point. And that would be covered in another section about a continuity of a function. Any questions? How we observe a limit from the graph? Okay. And also, certainly with the graph, very helpful. And in this case, the function we are considering here, it might be very weird. And one thing I want to know here is for sine function, it is a wave, right? The graph of sine and the cosines really are waves. And the sine, it is always bounded between -1 and +1. And then the thing is, we are having the graph of sine 1 over x. X approaching to 0, and 1 over 0 really it is not defined. So you can try some small values as x approaching to 0. And also, I did took this graph from textbook. What I'm trying to say here is I hope you see from the graph given, and basically as you can tell, as x approaching to 0, the graph of the function somewhat moves up and down. It oscillates very quickly between the upper bound 1 and the -1, 1 and the -1. So you cannot say x approaching to 0, this is sine 1 over x, it is approaching to anything at all, right? It just oscillates very quickly. So clearly, this is another case we are saying the function does not have a limit. This is another case we are saying the function does not have a limit. Thank you for watching.